Assalamualaikum warahmatullahi wabarakatuh, and very good morning to everyone. Good morning to all the delegates, presenters, participants. So welcome to the network and cyber security and also AI, artificial intelligence track of the International Conference of Artificial Intelligence and Autonomous System, i-CAIAS 2025. So today, my name is Nuruzaidah Niti Harun, and I'm honored to serve as the chair session for this session. So in this track, we will explore the convergence of network security frameworks as well as AI technologies. For all participants and all the presenter, I would like to inform that in this session we have 5 presenters that will present their works. So for this session, all presentation will be played as pre-recorded videos. Okay. However, if any presenter wishes to present live, so please inform us before we begin playing your video. All presenters are kindly requested to be ready for the Q&A session immediately after their presentation. So without further delay, let's begin our first presentation. Okay, so for the first title is Arima Gauge Based Time Series Analysis of Cryptocurrency Volatility. So the authors is Miss Husna Sarirah Hussein. Okay, I think this study applies Arima Gauge modeling to analyze the forecasting of cryptocurrency volatility. So maybe this title integrating statistic and AI-based forecasting approach to enhance the decision making. So before we proceed, may I check if Miss Husna Sarirah is present in this session? Miss Husna? Alright, okay. So now we will play the pre-recorded presentation by Miss Husna Sarirah Hussein for this paper. Thank you.
Welcome. Hi, I'm Hussein Sarirah Hussein. I'm from Universiti, and I'm pleased to share my latest research with you guys. So this is a collaborative work with my master student, Mr. Yap Kah Yong, and my other colleagues from Universiti as well, and other collaboration with Universiti Indonesia, Mr. Yodi, and Professor Lalita from Chennai, India. So this work investigates about the volatility pattern of cryptocurrencies using ARIMA combined with Gauge model to analyze historical price data of cryptocurrency and to predict and forecast future trends. So let's begin. So the overview of the presentation will cover the introduction, and then I will talk about some of the related work that we have performed, and then the methodology is of course using ARIMA for time series analysis. We will discuss the results and the findings, and finally the conclusion and future work. So cryptocurrencies have emerged as a revolutionary asset class characterized by their decentralized nature, high volatility, and rapid price fluctuations. So this paper will investigate the volatility pattern of major cryptocurrencies using autoregressive integrated moving average or ARIMA and combined with Gauge model to analyze historical price data and forecast future trends. Additionally, we also conduct a comprehensive volatility analysis to capture the inherent unpredictability of cryptocurrency market and perform seasonality analysis and calculated the RSI or relative strength index for the technical analysis indicator. So some of the related work that we have done is on the machine learning and advanced models, and we can see that recent research in cryptocurrency prediction, they use advanced machine learning and deep learning techniques such as LSTM models and hybrid approaches that combine with logistic regression, neural networks, and etc., and have demonstrated improved accuracy over traditional models like ARIMA. And however, some of the model performance is inconsistent. So comparative studies against the traditional ARIMA model, including time reverse and additive variants like Profit and NNER, show that no single model consistently emerged as the best performer for cryptocurrency price prediction. This highlights the complexity and non-linear nature of the market. And you can see that in a lot of studies, they have maintained that simpler models remain relevant. Even basic models like linear regression and random forest regression can achieve forecasting accuracy comparable to or sometimes better than traditional ARIMA models, underscoring the challenge of consistently outperforming simpler baselines in the volatile market. Okay, and since we are focusing on ARIMA is also can be the benchmark and interpretability tool. So despite the availability of advanced models, the ARIMA model remains important because of its simplicity, interpretability, and parsimony. So it serves as a strong, understandable benchmark against with the performance and added value of more sophisticated, often black box models are justified and compact. So let's look at the methodology or the research flow that we have performed in this research. So the first one, of course, we will download the data. And for this study, we use R. So we install the necessary R libraries and we convert the data to data frame and then convert to XDS object for time series analysis. Then we perform exploratory data analysis or EDA, where we find out the summary analysis. Okay, then after that, using R, we perform the time series modeling using ARIMA and also GARCH, as well as conditional volatility. We also perform technical analysis indicators using relative strength index, and then we look at the seasonality analysis, where we allow future updates or retraining based on user data. And finally, we benchmark our performance using annualized return and drawdown analysis. So let's look at the data set. So for the data set, we use the QuantMod package in R to download historical cryptocurrency from Yahoo Finance. So the data spans from 1st January 2020 to 18th of August 2025, and this include daily closing prices of selected cryptocurrencies. So the downloaded data had 1,632 rows and 6 columns, and the variable extracted from the data set include date, BTC USD open, high, low, close, and volume. So in the second stage, where we perform EDA, so we compute summary statistics such as mean, median, standard deviation for key variables like price and volume. And we also use ggplot, a package in R, to create visualization such as these line plots. And then we perform stationarity testing using statistical tests like the augmented Dickey Fuller or ADF test. We also perform volatility analysis to examine the volatility of the cryptocurrency by calculating daily log returns. And then we use ARIMA for our time series analysis. So to determine the optimal ARIMA, which is the PDQ parameters, we utilize the auto.arima function within the forecast package in R. So this function employs a systematic search algorithm to identify the best fitting model by minimizing the archaic key information criteria. So the AIC balances the model's goodness of fit with its complexity, ensuring that the selection of a parsimonious model that best represents the time series data. So this automated approach eliminates subjective manual selection and ensures a robust and statistically sound choice of parameters for our analysis. For the GARCH or generalized autoregressive conditional heteroscedasticity model, we use this together with ARIMA. So this hybrid approach of ARIMA and GARCH allowed for the modeling of both mean and variance dynamics in the time series. Okay, so let's talk about the results using this ARIMA model and also GACH. So first, we look at how they are able to capture the trends and forecasting prices. So the ARIMA model effectively identified both short-term fluctuations and long-term patterns in the time series data. So these metrics indicate that the ARIMA model is particularly adept at smoothing out noise while retaining essential price movement, making it a reliable tool for predicting future price trajectories. So you can see that in the diagram there. However, the model's performance vary during periods of extreme volatility as shown in this diagram here. You can see a very sharp down there. Okay, pose challenges to the predictive accuracy. So from the figure here, we can see that possible price of Bitcoin will move in the positive and negative direction. Okay, then we look at the periods of high volatility and potential causes. So the analysis revealed several periods of heightened volatility in the cryptocurrency market, characterized by sharp price swings and increased trading volumes. You can see how the graph here going down and going up again and going down, and here is going up. Right, so based on figure 8, we combine with volatility forecast and we can predict the direction of Bitcoin will go higher on 20th July 2025, 30 days from 20th June. And for your information, it did go higher. And then we look at the technical analysis indicators. So from this figure with the technical analysis, we can see that the Bitcoin is still able to go in future higher due to the trend is up. And the fast simple moving average, which is 50 days average, is above the slow simple moving average, which is 200 days moving average. So the opposite scenario will happen as bear market if the slow simple moving average is above the fast moving average. And then we look at the RSI or relative strength index. Okay, so from this figure here, we can see that the indicator having no significant effect on the Bitcoin moving. So this is because the strength cannot manipulate the large market cap of the Bitcoin. So to show that RSI has no significant effect, we have performed a quantitative analysis to show that there is a lag correlation between the RSI and Bitcoin's price movement. So we found that the Pearson correlation coefficient between the daily of RSI values and Bitcoin's daily returns is 0.05. So this value is being very close to 0, supports our claim that there is no significant linear relationship between the RSI and Bitcoin's price movement. Then we look at the seasonality analysis from the figure here. It is evident that the cryptocurrency prices tend to exhibit a favorable trend during the month of September. So if you are in the cryptocurrency market, right, you can see that September and October is going high. Furthermore, investing during this period demonstrate a high probability. So now it's already the end of October and it has proven that this seasonality analysis is accurate. So this pattern suggests recurring seasonal behavior that may inform strategic investment decisions within the cryptocurrency market. Then let's look at the performance metrics. So there are 3 performance metrics that we have done. The first one is the annualized return. So the annualized return of Bitcoin was calculated to be approximately 21.92%, representing the compounded daily returns extrapolated over a year. So this figure indicates that Bitcoin has historically demonstrated profitability, albeit with diminishing returns compared to its earlier years. For instance, during periods such as 2017 and 2020, Bitcoin exhibited annualized returns exceeding 100%, reflecting its volatile yet lucrative nature in specific market conditions. The second performance matrix is annualized Sharpe ratio. The Sharpe ratio, a measure of risk-adjusted return, was calculated to be 0.436 under the assumption of a zero risk-free rate. So this value
Of
indicates
course,
that
of
for
course, if you
every
can.
unit of risk undertaken, Bitcoin generated only
Okay.
0.436 units of return. So a sharp return below 1 is considered indicative of poor risk-adjusted performance, while ratios between 1 and 2 are
Sorry,
deemed
I
favorable.
think that this time
So
something
this
wrong
finding
with it.
aligns with the broader understanding of cryptocurrencies as speculative investment characterized by significant uncertainty and volatility. And the last performance metric is on annualized standard deviation. So the annualized standard deviation, a measure of volatility, was found to be 50.32%. So this metric quantifies the degree of price fluctuations in Bitcoin over a year. So a standard deviation of 50% implies that Bitcoin's price can potentially swing by plus minus 50% within a single year. For example, an investment of 10,000 in Bitcoin could realistically fluctuate between $5,000 and $15,000 annually. Such extreme volatility highlights the speculative nature of Bitcoin and underscores the importance of risk management strategies for investors that are engaging in cryptocurrency markets. So compared to traditional assets like stocks or bonds, which typically exhibit much lower volatility, Bitcoin standard deviation reflects its position as a high risk, high reward asset class. Okay, so based on those findings, we can see that the results of the ARIMA base time series analysis reveal a nuanced picture of Bitcoin's performance. While the annualized return of 21.92% positions Bitcoin as an attractive asset relative to traditional benchmarks like the S&P 500, its annualized standard deviation of 50.32% underscores the inherent risk associated with its price volatility. Furthermore, the Sharpe ratio of 0.436 highlights the inefficiency of Bitcoin in delivering commensurate rewards for the level of risk assumed by investors. So these findings emphasize the trade-off between potential gains and exposure to extreme price fluctuations, making Bitcoin a challenging yet intriguing asset for portfolio diversification. So in conclusion, the ARIMA model has successfully captured underlying trends and provided insights into periods of high volatility, which are often driven by factors such as regulatory changes, market sentiment, and macroeconomic developments. So beyond the core analysis, we also developed a versatile function capable of analyzing various cryptocurrencies and enabling a deeper exploration of seasonal price pattern, volatility prediction, and technical indicators. So this functionality allows traders and investors to assess the behavior of one cryptocurrency across different seasons or in relation to others, offering valuable insights into trading pairs and investment strategy. So this research not only contributes to the understanding of cryptocurrency price dynamic, but also provides a practical applications for traders and investors seeking to navigate this complex landscape with greater confidence. Thank you very much.
Okay, thank you so much, actually, Dr. Husna, for this presentation. Um,
Uh,
I have a
Elko, hi.
question.
Yes, please
Uh,
go ahead.
Alright. Could you share with us what are the factors contribute to the fluctuation of the Bitcoin price?
Liquidity, the supply of demand, and then also regulations. Okay, like I think there was few years ago, China they banned Bitcoin. So during that time, the Bitcoin price fluctuate. It went down really bad, and also sentiment driven, depending on the market and economy politics. So they are all external factors that can affect the market.
Okay. May I know how much the accuracy of your algorithm to detect or to calculate the forecasting of the Bitcoin prices?
Okay, we completed this paper in August, and then there was, remember in one of my slide about seasonality analysis, so it predicted that September and October the prices will go up, and true enough it goes up until now for September and October. So
Okay,
it's quite accurate, inshallah.
inshallah. Okay.
Uh-huh.
Thank you so much for the
Thank
presentation.
you.
Now we open onto the floor for a few questions from the audience. So, any question from the audience? Any question? Okay. Alright, waiting for the question, but I think there are no question. Okay, so thank you once
Thank
again
you.
for the paper presentation. Your contribution is so much highly appreciated. So let's now proceed to the next presentation. The next title is about integrating communication constructs in prediction motivation theory, modeling the impact of fraud awareness campaign by Dr. Akhiari Nasir. May I confirm if Dr. Akhiari Nasir is now, with us now?
Yes, yes.
Dr. Akhiari?
Yeah, yeah, Doctor.
Okay,
Yes. Okay.
alright. Okay, so we will proceed with your pre-recorded presentation, Doctor.
Okay. Proceed.
Alright. Okay, thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Akhiari Nasir, and I would like to present our paper, and the title of the paper is Integrating Communication Constructs into Protection Motivation Theory, Modeling the Impact of Fraud Awareness Campaign. As for the introduction, as we know that fraud and online scams have become a critical global concern, causing billions of dollars in losses annually and making people lose trust in the digital system. In Malaysia, several agencies have implemented a range of countermeasures, including public awareness campaign, SMS alert, and regulatory enforcement. Among others, the government have also launched the campaign of Tak Nak Scam, Jangan Kena Scam Fest, National Response Center, NSRC 997, and many more. However, despite continuous efforts by government and institutions, the incident of financial scams and cyber fraud continues to rise. The persistence of this threat shows that technical and legal measures alone may not change user behaviors behind scam vulnerability. While PMT has demonstrated considerable explanatory power in various domains, its application to scam and fraud prevention, especially in evaluating public communication efforts, remains unrelevant. Existing studies often isolate individual predictors without integrating them into a comprehensive framework. Therefore, given this limitation, there is a need to formulate a conceptual model that synthesizes the cognitive structure of PMT with contextual and communicative factors identified in previous studies. PMT has been applied successfully in areas such as health behavior, information security, phishing prevention, and social engineering. PMT posits that threat appraisal, which are perceived severity, vulnerability, and rewards, and coping appraisal, which are self-efficacy, response efficacy, and response cost, combine to influence protective behavior. PMT model has been widely applied in health psychology and cybersecurity, showing strong predictive validity across content. For example, study number 14 demonstrated that PMT construct significantly predicted online safety behavior among internet users, while study number 15 identified PMT as one of the most frequently used and impactful models in information system security research. While PMT has demonstrated considerable utility in predicting behavior, recent studies suggest PMT effectiveness can be enhanced by incorporating communication-based variable. For example, Tawalbeh and Muhidat 2023 found that the effectiveness of security awareness messages was significantly influenced by how well recipients understood and trusted the message source. Similarly, Ghazali et al. 2023 developed a PMT-based instrument that included message comprehension and credibility, and concluding that these elements were essential to translating risk perception into behavioral intention. In the Malaysia context, a qualitative study based on knowledge attitude practice or KAP by Azmi 2025 echo these findings by showing that campaign messages often lack clarity of trustworthiness, limiting their influence on protective action. Therefore, all these observations and findings support the argument that campaign design, particularly exposure frequency, clarity, and source credibility, must be better integrated into theoretical frameworks to explain how individuals respond to scam-related threats. Okay, this is the methodology used in this study, and there are 4 stages. The first stage is we adopt protection motivation theory as theoretical base. Then we focus only on threat appraisal. Okay. Number 2 is or stage number 2 is we integrate campaign construct, which are the message exposure, message comprehension, and message credibility into the PMT, and then we develop all the hypotheses that have relationship in the model, and then we propose extended PMT research model. Okay, these are all the hypotheses proposed in the study. As we can see that there are 10 hypotheses in the study, and all of these hypotheses are supported from the previous study from the literature. For example, H1 hypothesized that campaign exposure will influence persistency, and this support by the study from number 23 and 34 from our paper that mentioned that frequent exposure increase recognition of threat seriousness. From these 10 hypotheses, there are 8 direct relationship and 2 mediation relationship. These are the result of our study, and this figure show the research model for evaluating the effectiveness of government campaigns in scam and fraud prevention. As we can see that there are 8 relationship, which is direct relationship, campaign exposure, message comprehension, and message credibility are hypothesized to influence perceived severity and perceived vulnerability, which in turn will influence protective behavioral intention. This is the mediation model for perceived severity, and the figure show the model for this relationship, and this suggests that the relationship between campaign exposure, message comprehension, and message credibility towards protective behavioral intention are mediated by perceived severity. As for second mediation model, which is mediation model for perceived vulnerability, this relationship suggests that perceived vulnerability mediates the relationship between campaign exposure, message comprehension, and message credibility with protective behavioral intention. So, as for the discussion, by incorporating the communication inputs as antecedents to threat appraisal, the model captures the entire cognitive behavioral pathway from message reception to intention formation. The structure of the model is supported by existing theoretical work that emphasize the need to conceptualize PMT within broader persuasive communication frameworks. The equation of both cognitive appraisal and external message factors provide a more complete picture of how individuals respond to government-led anti-scam effort. And this is supported by a study number 7 and number 29. This model also allows researchers and practitioners to evaluate not only whether campaign work, but also how and why they influence behavior motivation. The integration of campaign exposure, comprehension and credibility demonstrate that protective intention do not arise solely from internal appraisal but are triggered by external communication inputs. So for the mediation analysis involve perceived severity reinforce the theoretical expectation that behavioral intention are activated through recognition of the seriousness of fraud threats. The inclusion of vulnerability as a mediator underscore the importance of crafting campaign messages that encourage individuals to internalize the risk and perceive it as a personal relevant. The second motivation pathway through perceived vulnerability emphasizes that recognizing a threat's seriousness is insufficient unless individuals also view themselves as potential victims. So the contribution of this paper is uh, twofold. First, it addresses a significant gap in the literature by linking message level variables to cognitive processes and behavioral outcomes. Unlike previous studies that assess PMT in isolation from communication context, the proposed model captures the complete cognitive sequence from message reception to intention formation. Secondly, it offers a practical structure that can guide empirical investigation and inform campaign design. By identifying perceived severity and vulnerability as mediators, the models help diagnose which elements of a campaign are most effective in activating protective motivation. In conclusion, recognizing the growing sophistication and impact of these threats, the model was extended to incorporate three critical communication constructs, which are campaign exposure, message comprehension, and message credibility, as external antecedent to threat appraisal. By integrating this construct with the PMT dimension of perceived severity and perceived vulnerability, the model offers a theoretical grounded framework to explain how public messages influence protective behavioral intention. The proposed model contributes both theoretically and practically to the field of cybersecurity awareness, behavioral science, and public policy. Lastly, it provides a solid foundation for future empirical work and supports the design of more targeted and psychologically effective government campaigns against scams and fraud. So that's all. Thank you.
Thank you so much, Dr. Akhiari Nasir, for this presentation. So I think the findings of this research highlight how fraud awareness campaign influence individual protective behavior against online scam. Okay, so before we proceed to the Q&A question, I have my own question, Doctor. Are you there?
Yes.
Alright. So where do you plan to apply this PMT theory? In any government sector or any place?
Okay, this is only the conceptual model for us to proceed to the design of the questionnaire in order to get the data collection and then analyze and to see the effectiveness of message campaign in activating the cognitive intention to protect from the scam or fraud. So when you ask regarding the how to apply to the government, it's not like that. It's just for the time being is only to use as a theoretical background for this study.
Okay, alright. Okay, so we have another two questions from the
Okay.
audience. So the first one, how was the effectiveness of fraud awareness campaigns measured in terms of behavioral change rather than just awareness level?
Okay,
So
we
what was
as
that?
the when the result and analysis of this research will publish, we can see how the message campaign in terms of message comprehension, campaign exposure, and message credibility will influence the individual's protective behavior. So that by this research, we could design an effective message campaign to trigger or to activate the people to protect from scam. Okay, that's all.
Okay, understand. Alright. So the second question is, which of the three campaign constructs exposure, the first one, comprehension and credibility, had the strongest significant effect of
Okay,
the perceived vulnerability in the
as
Mukos model?
I told just now, this is for the first stage. The second stage is the data collection, and then after that, data analysis. So we don't have any result yet, but from our experience in information security awareness, uh, among three these construct, which is exposure, comprehension, and credibility, the most significant one is the two, which is comprehension and credibility. Mean to say that the message must be understand by the individuals, and the message should be valid and accurate, so that they are will protect themselves from this scam and fraud.
Right, okay, okay. So we understand about your research, and once again, thank you so much
Very,
for
thank
your
you, thank you,
insightful
thank you, Nata.
contribution.
Right.
Okay, all right. You're welcome. So we move to the next presentation, which is the third paper. So the paper ID number is 38. Enhancing digital evidence analysis, fake seeker for real-time deepfake detector using efficient net. Okay, the author is Mr. Chua Kaizen. Mr. Chua Kaizen, are you ready for the Q&A session right after your presentation?
Yeah, I'm ready.
Okay, you're ready. So actually, I think this paper address about the growing challenge of deepfake technology and its impact on digital authenticity and forensic integrity. So we will proceed with the pre-recorded presentation by Mr. Chua Kaizen. Thank you.
Good morning, everyone. My name is Chua Kaizen, and today I'm going to present Enhancing Digital Evidence Analysis Fake Seeker for Real-Time Deepfake Detector using EfficientNet. So for this video, going to involve introduction, redacted work, methodology, result and detection, and conclusion of this research paper. So we are facing a critical challenge in our digital integrity, which is deepfake. So what is deepfake? Deepfake is a technology refers to media created using deep learning techniques to alter or replace faces in their image or video. In recent years, deepfake technology, which utilize advanced deep learning techniques to manipulate videos and image content, has emerged as significant digital phenomenon. This technology is a critical social threat, causing a erosion of trust in digital media, spreading disinformation, and embedding fraud. So recently, 29 reports are filed against students for creating and distributing deepfake image for other students, which highlighting the urgent of needs for the reliable detection. So for forensic investigator, they require a repeat and reliable tool to verify media authenticity. However, many existing detection tools struggle to keep pace with new technology, which require extensive computational resource, which limit their use in the field and creating a need of lightweight, efficient, and reliable tool that can run on a standard forensics workstation without relying to the cloud. So to fill this gap, we developed FakeSeeker. FakeSeeker is a lightweight real-time defect detector designed specifically for digital forensic investigation. Our objective was to create a practical application that can analyze both uploaded files and live video stream in real time. The core of our tool is a fine-tuned EfficientNet B0 model, which we choose for its perfect balance in high accuracy and low computational cost. To position our work, we conduct a review of the current state-of-the-art model. As this table shows, we found that many powerful and highly accurate approach, for example, like multi-model approach, which combining video and audio analysis to achieve high accuracy, and also use advanced transformer to find tiny inconsistencies between video frames. Also, we saw hybrid models like using CNN with RNN structure, and also cascade models, which combine InfiniNet and transformer together. But as you can see, the limitation column, we identified a critical problem. While these models are accurate, but their architecture, complexity, secure processing, and high computational demands make them unsuitable for practical and real-time forensic work. This analysis confirm our mission, which is urgent needs for a tool that not only accurate, also lightweight, efficient, fast enough for on-site. So we choose InfiniNet because it innovates compiling scaling method. It allows to achieve superior accuracy with significance of fewer parameters and lower communication costs. It is ideal for the choice, which being lightweight and practical tool. So how did we build it? As you can see from the diagram, FSKTM is a modular system with 4 key parts, which the first part is the media processing module, takes the user upload of all live camera feeds. The second is the face extractor, which uses MTCN to find and isolate every faces. And the third part is our defect detector engine, which is the trained InfiniNet model, which classifies each face as real or fake. Finally, the reporting module generates a detailed forensic report. A great model needs a great data. We combine the largest public dataset, which is severity DF, Face Forensics Plus, and the FTC prepared by the Meta. This gives us a massive, diverse set of real examples. After processing and extracting all the faces, our final data sets contains over 200,000 processes face for training and testing. Also, our training architecture, which is the key to our success, we started with a standard 80 to 20 train test split. Then we apply the data augmentation like random flip, rotation, and color jitter to make the model more robust against the fake that haven't seen before. So finally, we use the fine-tuning strategy. Instead of training from scratch, we use the pre-trained InfiniNet model and strategically unfrozen the final layer. This approach is much more faster and lead to better performance. Now for the result, we have tested 3 InfiniNet variants, which is B0, B1, and B2. This is because the number of dataset only sufficient for these 3 models. So the data is clear. InfiniNet B0 provided the best balance of speed and performance. It was a faster training at only 9 minutes for each epoch, and it achieved a higher accuracy at 99.2%, and it has a lower validation loss. It means that the most confident in its prediction. Looking closer at our final B0 model, the performance is excellent. We achieved a final test accuracy of 99.2% and an area of under the curve, which is the AUC, it's 0.9996. As you can see at the learning curve on the left, it also states that the training was stable and it does not overfitting. And also, the confusion matrix on the right also confirms the extremely low number of errors with the near perfect precision and recall. So we also compare our model to recent year 2024 study by Singh et al. That also used EfficientNet B0. Their model achieved 76.3% accuracy, but our model, physical model, also in the same B0 architecture, achieved 99.2% accuracy. The reason why this is a massive improvement is our significantly larger and more diverse dataset. Over 160,000 training images compared to their 800. And our specialized fine-tuning pipelines help the accuracy improve a lot. And here is the final product. FakeSeeker is a complete and standalone application. This is the main page of the application. As you can see, there is a upload image and real-time detection, and also a view scan history selection. So for upload media selection, user can upload media for analysis. As you can see, they can select file. After select file, you can click the start or cancel the scan. So this is one of the real-time detections which using the camera feeds. As you can see, there's a green box which is stating which is real or fake for the image collected. So the next one is the real-time detection, which using the screen recording. As you can see, there is the selection of start detection, stop, and show the status, and or get back to the main window. After that, the third selection is to view all the scan history, which can review all the past scan in the history page. The tool generates detailed forensic report that include all the metadata like timestamp and file path that an investigator needs. Finally, we prove it's truly lightweight. The application starts under 10 seconds. It can scan a large 150 MB high definition video in only 15 seconds, and during a real active detection, it keeps low profile, peaking only at 30% CPU usage. It confirms that highly efficient and suitable for any standard forensic workstations. As you can see, all the small image to the large image, it's used to 2 seconds to 50 seconds. And also the memory usage of the CPU does not change very much when the real-time screen during detection. In conclusion, we successfully design, develop, and evaluate FakeSeeker, a tool which optimizes for digital forensic. We achieved 99.2% accuracy using an EfficientNet B0 model. We built a complete standalone application that can provide a repeat real-time analysis. Also proven it's lightweight and practical screening tool that empowered investigators in the field. So our contribution is a highly practical, high-performance tool that fill the critical gap for the forensic investigator. So for the future work, we plan to develop a web-based version for a greater accessibility. The most important, we implement a system to continuous model retraining. This is crucial for maintaining the robustness against a new different technology that are merging every day. And finally, thanks for your time.
Okay, so thank you so much, Mr. Chua Kaizen, for that interesting presentation on your apps, FakeSeeker. So I think FakeSeeker represent an important advancement in ensuring the authenticity of digital evidence. Mr. Kaizen, are you here?
Yeah.
Okay, I have a question. Can you give a reason why EfficientNet B0 outperform the other variants in terms of overall performance metrics?
So thank you for the question. So why B0 is better than other model is because it use lesser parameter and balance between efficiency and accuracy when compared to other CNN models. So got a lot of paper prove that benchmark uh, EfficientNet is using a better method which called compound scaling to balance the computational cost to get a better accuracy.
I have another two questions here in chat. So the first one is, how do you ensure the model remains effective as deepfake generation technology continues to evolve?
So to ensure the model remain effective, so our paper concludes that continuous model retraining with a newer and more diverse data set because nowadays you can see a lot of generator or AI can make so realistic deepfake. So even human can differentiate it. So we need to use more diverse data set to train our model. So next is including the emerging deepfake generator techniques and also uh, maintaining the detection robustness.
We have another one. Last question. Compared to the resource intensive tools mentioned in your study, what is the quantifiable improvement in computational resources? For example, speed, memory usage that makes fake seeker lightweight.
All right. So how to prove that FlexSeeker is lightweight is the application startup time. So we calculated the tool launch and is ready to use is consistently below 10 seconds. And it can rapidly scan speed in 2 seconds in for small image. For big image, like about 5 MB is 3 seconds. For large and long HD video, about 150 MB is about 15 seconds for processing. So also for the low CPU usage, so about like CPU usage about like 11% to 80% during file scanning. For the real-time detection is about 22% to 30%. Yeah.
Okay, thank you so much, Mr. Kaizen, for your impactful work and demonstration. All right, thank you. So we will now proceed to the fourth presentation. Okay, the paper ID is 88. Okay, also pre-recorded, played. Okay. So the title is Studying Age Relationship in Homogeneous Graph-Based Insider Threat Detection by Mr. John Zhu An Chung. Okay, so I think this paper focus on insider threat detection and by modeling the relationship between the users and their activities. Mr. John, are you here to be ready for the Q&A session right after your video
Hello.
presentation?
Yep,
Hello?
I'm here. Hello. Yeah, can you hear me?
Ah, all right,
Yes, I'm here.
okay. Okay, so now we will play the pre-recorded presentation prepared by Mr. John to demonstrate their findings for this paper. Thank you.
Hello, everyone. Welcome. And today I'll be presenting our research titled Studying Edge Relationship in Homogeneous Graph-Based Insider Threat Detection. So before we delve into our research itself, let's go through a bit of the background and motivation as to what triggered us to conduct this study. So if you have a look at the statistics on screen, right? This is a study done by the Ponemon Institute studying on the cost of mitigating insider threats. And you can see that from 2018, 8 million USD it has risen to 2022's 15 million USD, and this is a rising trend. And another study done by Spearnix, right? They polled organizations and they find that about 90% find insider attacks equally or more challenging to detect compared to external cyber attacks. So what is insider attacks, right? Insiders are basically employees within an organization, right? They already have authorization to a certain degree. They know your SOPs. They know what application, what services you are running. So they can more easily, right, conduct any attacks on your organization itself, right? Compared to external cyber attacks, whereby they have to go through hoops, reconnaissance, finding out what are the vulnerable areas. Insiders already have, to a certain degree, some of the knowledge, right? And why are we going towards graph-based, right? If you think about log data, right, which is what we would use to detect insiders, right? We look at log data, you would probably think of models like RNN, LSTM, or even transformer, right? So why graph neural network, right? This is because we are trying to explore, right, the possibility of using graph neural network, right? Much like LLMs, which has gained interest within the past few months, right? Within the past few years, right? So we are trying to explore, can we use, graph neural network, much like how LLMs is being applied to a lot of the scenarios nowadays, right? Can we use GNN to apply into our insider threat detection scenario? So there is already existing studies that have studied on the standard detection methodologies, right? Using RNN, LSTM, transformer, CNN. All these have been covered quite extensively, but as for graph-based approaches, right, we only find about 22 literature through our Scopus and also Web of Science search, right? And each of these literature approach the detection in a different manner. So there is two sets of node type representation. We have the homogeneous graph as well as the heterogeneous graph, which I'll go through in a bit more, right? And each of these studies uses different approaches of data balancing and edge connections, right? They're all trying to innovate with novel models, right? But they miss out on some of the more fundamental things, right? Like different data balancing and also edge connections used. So what are homogeneous graphs, right? Homogeneous graphs are of nodes of the same type within the same graph, right? They aggregate and group the features whereby they are condensing the number of nodes to reduce the imbalance effect, right? Because within a day itself, right? So commonly in insider threats, right, we condense the data, the features itself based on user days, right? That's a homogeneous node, right? So we would have this user, one day they might have about 10,000 activity, right? But with homogeneous graph, we condense that 10,000 potential nodes into a single node, right? And the edge types that we have found is, for example, device sharing, whereby if they share the same device, there will be an edge built between them. If they have sent email communications with one another, there will be edge formed between them. If they are of the same user hierarchy, right? If they share the same supervisor, if they're in the same team, there is a edge formed between them. There's also feature distance based, whereby they calculate the features similarity and form edges based on that. Right? So the pros is that it has lower memory and computational requirement, right? Because it already condensed the number of nodes, right? But the cons is, of course, it loses cross-domain and temporal nuances, right? Because if we were to have it separate, different activity, we can easily identify, right? Which node type is it? Is it a file activity that is flagged as insider, or is it a web browsing that's flagged as insider, right? So what about heterogeneous graph, right? Heterogeneous graph are of different node types, as you can see on screen, right? So the primary focus of it is for real-time activity inside the threat detection, right? So you can see that, it is connected of different node types. So there is file node types, right? Log on node type, device, web browsing, So the imbalance is very obvious because, as I've mentioned, right, a single day a user can generate about 10,000 activity, right? And the edge type that they have used is, for example, feature distance, right? Temporal, whereby perhaps if they share the same device or if they share a certain supervisor, for example, there is edge form between that. There's also sequential, right? Whereby um, within the chronological events, right, there is an edge form based on that. Of course, the pros is that it has a richer context and better anomaly capture, whereby we can specifically identify if a node is detected to be an insider, we can immediately investigate that particular activity, right? Whereas with homogeneous, we have to go through that day's the user's daily activity to go through, which possibly would be the insider. Of course, the cons is that it requires a higher resource demand, right? So the research gap that we are trying to fill is that there is a lack of study on the data balancing techniques in graph context, right? We can just use mode to, upsample, for example, but then what about the edges, right? Smoke doesn't recreate the edges, right? So we are looking into that area, right? The data balancing techniques, how does it affect the model performance? And secondly, we want to fill the gap of the lack of study on efficacy of the different edge connection, right? Different literature uses different edge relationship already. So we are trying to study which edge relationship perhaps would give a better performance. And lastly, there is a lack of the open source code, whereby with our study, we are open sourcing our code to contribute back so that researchers can get into the insider threat detection, especially in graph-based scenario, with a lower barrier, right? The dataset that we'll be using is the CERT-CMU dataset, right? Primarily, we're using the CERT R4.2, right, which is a dense needle. So they are all highly imbalanced, simulating the real-life scenario, right? And of course, as I mentioned, different literature use different graph construction approach. If we look at the R4.2 distribution ratio, right, if we were to approach this using the heterogeneous way, right, you would see that there is a challenge that we need to tackle is that the file node type, right, there's only about 10 file node types that are malicious throughout these 17 months of data, right, which is quite challenging. So in this case, right, we are only focusing on the homogeneous. Of course, we are also studying on heterogeneous, but that is a separate research paper altogether, right? And for this research paper, we are focusing on the homogeneous itself, right? So the three edge relationship that we are studying is the device sharing, email communication, and user hierarchy, as I've mentioned previously, right? So we use REST HypeNet, an existing model, right, which is a hybrid CNN with GNN detection model. This is their architecture, right? And we build upon that by adding not direct embeddings, Laplacian eigenvector positional encoding. We do mini batching as well using Metis clustering, and we added the jumping knowledge, right? So we call this architecture itself enhanced REST HypeNet, as we are building upon the REST HypeNet architecture, right? And if you look at the results that we have, right, for the undersampling and oversampling, right? For oversampling, we are using the graphs mode. So there is a existing algorithm, graphs mode, that is similar to SMOD, which recreates, right, edge relationship, the edges as well based on the SMOD calculation, right? And you can see that in the undersampling and oversampling, we have about half of our enhanced version having a better performance compared to the original REST HypeNet. And within the 1 month, right, we can see that only one scenario whereby the CNNJT with device edge has a lower performance, and the rest of the scenarios, right, they actually have a better performance compared to the original baseline, right? So we also benchmark the enhanced REST HypeNet against the original study where we have extracted the edge relationship. And we are proud to say that in terms of the three edge relationships, our model itself had a better score compared to the original study, right? Of course, with the REST HypeNet one, just the REST HypeNet with the clustering was able to achieve better performance compared to the original baseline without clustering. But of course, we are comparing this directly to one another because we are using, for for example, GCN to GCN and JT to JT, right? But of course, within our model itself, actually, we find that for homogeneous graph itself, right, SAGE is actually the most performant backbone. So because this study itself, we are using 3 GNN backbones. We have GCN, JT, and SAGE, right? We actually find that SAGE provided the best performance across the 3 different backbones. And of course, the benchmark that is shown here is comparing apples to apples, right? We are comparing the same backbone to the same backbone. However, right, if we were to include our SAGE results, it will be much better than this, right? And overall, right, we can find that by ranking our performance of the different models and across the different edge relationship, we can find that for enhanced REST type net, right, email performed the best, and for REST type net itself, user performed the best, right? And through this, right, we can see that, of course, it is based on the model as well. So to conclude, right, we have contributed the enhanced REST net, a improved hybrid GNN architecture. We have also done the edge relationship comparison. So our framework itself also allows for edge relationship comparison, right? And what we gather is that from undersampling, we can also deduce which edge relationship would be the most effective when convert to the 1 month scenario, right? Because 1 month is the one without any sampling, any data balancing done on it, right? And architectural sensitivity, it shows that the impact of edge relationship across different GNN architecture will vary, right? And of course, we identify that we can use device-based edge, right, as a stable and reliable baseline. So we can know that, the baseline would be the one, the performance that is set by the device edge relationship. So that means we have room for improvement, right? So if we use device as a baseline, then if we see, perhaps if we use either email or user, we can perhaps have a better performance. And of course, the limitations and the future works, right? This limitation itself of this research is that we are primarily focusing on simulated data sets, right, which may not capture all the complexity of the real world organization environments, right? Because insider threat is such a privacy laden topic, right? Usually organizations will not be willing to share their log data with us, right? And of course, we have limited validation on large scale operational ITD systems. On the future works wise, we would probably recommend to incorporate LLMs or NLP integration, because within this study itself, we did not use the linguistic features, right? So incorporating that perhaps could better improve our models, right? And of course, extend this framework for scalability and deployment, right? And lastly, optimization to optimize the computational efficiency, either in the calculation parts or using certain optimization techniques, right? Lowering the, condensing the feature set even more, perhaps, right? So that is all for our presentation. Thank you for listening in.
Okay, thank you so much for the technically rich presentation. So basically, this research used graph-based model for insider threat detection. So particularly related to AI to uncover the subtle behavior relationship within organization networks. So, Mr. John, now we open to the floor for the question. So I will check in the call messages. So the first question is, could this graph-based approach be extended to heterogeneous networks or multi-layer security data sources?
Okay, so thank you for the question. Yes, so in this study itself, particularly for this paper, we are focusing on homogeneous interpretation of our model, right? But of course, if we were to include the heterogeneous one in, it will be a very confusing for both the readers to interpret, because we are focusing on homogeneous and also heterogeneous at the same time. You might get confused on the models and the interpretation of data. But yes, of course, I'm doing my master's at the moment. So the homogeneous is the first part of my study, the heterogeneous one is the second part of my study. And yes, it can be extended into heterogeneous network because we are also studying at this point using heterogeneous graph-based neural network to perform the insider threat detection. But of course, as I've mentioned in the presentation itself, because the imbalance itself will play a role in our model performance, because with heterogeneous is not as condensed as the homogeneous data set, the data itself, the nodes. So the performance is a bit deteriorated from there, but of course we are trying to see if there are any algorithms that we can put into use to improve that performance.
Okay, thank you so much for your explanation. Yeah, maybe your scope now is for a heterogeneous
Yeah.
network. So maybe next time you will improve it to
Yes.
heterogeneous network. All right. So we have another question. Second question is, why did the user and email relationship models, both using GCN, significantly outperform the device relationship model using GAT in F1 score? For example, let's say 0.59 and also 0.95 versus 0.91.
Okay, so thank you for your question. Right, so the three backbones that we use for this study itself is GCN, GAT, and also SAGE. So graph convolutional network, graph attention network, and also graph SAGE. So for graph attention network itself, it is also weighing the edges that is formed with attention. So it is assigning attention to the different edge itself. So because it is homogeneous, because everything is already condensed into the single node. So in this study itself, actually, we find that JT does not perform as well as GCN or SAGE, because SAGE itself aggregates the neighbor features and performs the detection and learns the embedding from the features itself. So actually, SAGE performed relatively well in our study for homogeneous. But of course, actually, I'll just share some insights from our heterogeneous study, right? So in terms of heterogeneous study, JT is actually the one that has the highest performance at this stage, because GAT itself has attention, give attention to the edges, right? So in terms of heterogeneous, because each node itself is a different activity, right? So each activity itself has a different implication in terms of your insider activity. So with attention itself, then it can better identify the insider classification. Yeah, so I hope that answers your question.
Okay, alright. I think that is a good explanation based on the result of either GCN and also
Yes.
GAT. Okay, okay. So thank you so much, Mr. John. Thank you again for your excellent presentation and your participation. Thank you. All right.
Thank you, everyone.
So, okay, you're welcome. So, we now move to our final paper for this session. So the final paper is 69. So the title is Fault Tolerance and Secure Replication in Distributed Databases, BVAG-CR approach to handle neighbor replica failures. So the author is Miss Sharifah Hafizah Ahmad Ubaidillah. So I think this paper is about binary vote assignment on grid with checkpoint and rollback recovery. So the abbreviation is BVAGRC. GCR, So designed to enhance the fault tolerance, consistency and availability. So before we begin our presentation with pre-recorded, so let me check first. Either Dr. Sharifah. Dr. Sharifah Hafizah, are you here? Dr. Sharifah is not available here. Okay, if not, we just play lah whatever the pre-recorded video prepared by Dr. Sharifah. Okay, so we begin the presentation with the pre-recorded video. Thank you.
Assalamualaikum. My name is Sharifah Fiza binti Ahmad Badila. I am a PhD student from Universiti Malaysia Pahang, Sultan Abdullah. So today I would like to present my research paper entitled Fault Tolerance and Secure Replication in Distributed Databases, a BVAGCR approach to handle neighbor replica failures. In distributed database systems, replication is an essential element for improving fault tolerance, availability, and performance by deploying redundancy copies or replicas of data across different nodes or sites. This redundancy ensures that operations can continue even if individual components fail. However, maintaining availability and consistency becomes increasingly challenging when replicas fail during active operations, particularly in structured topologies such as ring, grid, or chain-based systems. In these environments, neighboring replicas depend on direct interactions with one another to propagate updates and maintain synchronization. When a neighbor replica fails, local consensus mechanism, quorum-based updates, or chain replication processes may be disrupted, leaving replicas in an inconsistent or stale state and threatening the reliability of ongoing transactions. When replication relies on the intermediary nodes for updates, delivery, or acknowledgement. These instructions underline the importance of effective fault tolerance mechanisms that can handle failure detection and reposition rapidly. To address this challenge, fault-tolerant approach such as checkpointing and rollback recovery have been widely applied in distributed and parallel systems. Checkpointing periodically stores the current system state, while rollback recovery restores the most recent consistent checkpoint upon failure, avoiding the need to re-execute entire transactions. This mechanism reduces execution delays and minimizes data loss during failure recovery. Several prior studies have examined the integration of replication with CR in different domains. For example, paper by Matanzati and Senhaji demonstrate that replication combined with coordinate checkpointing could enhance recovery in parallel message passing and grid system by preserving execution state and reducing rollback overhead. Similarly, Zhou and Yuval in 2021 optimized checkpoint intervals for multiprocessor workloads, showing that fine-tuned CR policies can reduce checkpointing costs while ensuring consistent recovery. This approach highlights the strength of CR for improving recovery efficiency. However, they generally require waiting for failed site to recover, which prolongs downtime and increases execution latency. Compared to these studies, the present work enhanced the binary word assignment on grid protocol by integrating CR into its transaction management framework. The enhanced model referred to as BVAG-CR is managed through the binary word assignment on grid with checkpoint and rollback recovery transaction manager. By combining BVAG structured voting-based replication with CR state-based recovery, BVAG-CR aims to reduce execution time, ensure consistency transaction recovery, and improve overall fault tolerance in the presence of neighbor replica failures. Unlike earlier works that focus exclusively on CR, this study explicitly situates CR within a database replication protocol, demonstrating its impact on execution efficiency and resilience in distributed database environments. There are 8 phases involved in BVAG-CRTM, which are initiate log, propagate log, obtain quorum, check quorum, update, commit replication, unlock, and release log. In each phase, the status of each site is saved in a checkpoint file. This figure shows the process diagram of BVAG-CRTM database replication transaction. A newly built database replication transaction, which requests to update data, is in the first queue in BVAG-CRTM. First, the transaction determines whether the primary replica site containing the data was free, busy, or experiencing a failure. This step is known as initiate log. If the PR site is free to use, which means the status is 0, in the transaction, the status will be set to 1 and the number of quorums W will increase by 1. Otherwise, the primary site will be released since it is unavailable, commonly known as the release log phase. The status of the PR sites and data that need to be updated are saved in the checkpoint file. Next, the transaction tries to log all the neighbor replica sites. This phase is called as propagate log. Each time the neighbor replica site gets logged as 1, the number of quorums is increasing. The obtained quorum, which is in the obtained quorum phase. Once the number of quorum is equal to the number of sites needed for the transaction to proceed, the application transaction can be proceeded as in check quorum phase. However, if the amount of quorum is not equal to the amount needed for the transaction, thus all neighbor replica sites are released from the transaction. Next, after all replicas have been logged, the update phase executes. The particular data is updated at primary database, which is situated in the primary sites. The primary database is then saved. The updated primary database is then saved in the checkpoint file. Afterward, the update data is replicated to all neighbor replica database. This process is called as commit replication phase. All neighbor replica database were then saved in the checkpoint file. Lastly, the unlock phase started. The status of the primary sites and all neighbor replica sites are unlocked, which means that the status is set to 0. If the checkpoint file is detected, that means there is an error occur in the particular transaction. The checkpoint file can only be retrieved if the transaction has been restarted after a site failure has been solved. The information that has been saved in the checkpoint file are the status of the primary replica and the status of all neighbor replica, the data that need to be updated, the number of quorum, the primary replica database, and all the neighbor replica database. The status of PR and all neighbor replica is then set as 1 to declare that it is in use for the transaction. Later, the process of updating data in the database of the primary replica, which is located at the primary replica site, was carried out. The update procedure was subsequently recorded in the file named checkpoint file. Afterward, the update data is replicated to all neighbor replica database as in checkpoint recovery phase. All neighbor replica database were then saved in checkpoint file. Lastly, the status of primary replica and all neighbor replica are unlocked, and the status of each site is set to 0 as in unlock phase. Then, the checkpoint file will be deleted. This table shows the experiment transaction flow. There are maximum number of 5 sites involved in this transaction, which is situated in form of 3 times 3 grid structure. Site E is considered to be the primary replica, having the primary data E in the present inquiry. Sites B, D, F, and H are the adjacent replicas that will receive a copy of the data from site E. The data E should be updated and duplicated into the replica of the neighbor according to the transaction T. Based on the table, the transaction of T started at time corresponding to 1, T1. It asks for the site E to update data E. Site E was logged by a transaction at time T2. As a result, the status of site E was preserved in the checkpoint file and is currently equal to 1. There was now 1 in the quorum. For data E at its neighboring sites B, D, F, and H. The transaction T propagate log from T5 to T18. The state of each neighboring site was recorded in the checkpoint file, and 1 was added to the quorum each time the neighbor sites were logged. If there was a sufficient quorum to continue the transaction, as in T19 and T20, the update procedure was carried out. All the sites, primary replica and neighbor replica sites, were however released from the transaction if there were enough quorums. As in this instance, there were enough quorums to move on with the transaction. Additionally, the number of quorums was preserved in the checkpoint file. The process of updating the data in database E situated at site E then starts at time T22. But when updating the specific data, failure happened as in T23. The status of each site participating in the transaction was set to -1, as can be seen in T24, indicating that one of the sites experienced an error. One of the neighbor application, notably site B, experienced failure for this experiment. Then, the recovery process started right away at T25. Following the completion of the recovery procedure, the information pertinent to the ongoing transaction was obtained from the checkpoint file, and the transaction was restarted at T26. After the transaction was restarted, all rated sites had their status update to 1, which means busy or in use, much like in T27. The checkpoint file in T28 was then used to store the status of all sites once more. Later, the procedure of updating the data E in the database E located at site E was once more carried out, as in T29. Due to an incomplete updating procedure at the time the problem occurred, the process had to be complete. The update procedure was subsequently recorded in the file with timestamp T30 and saved in the checkpoint file. The commit replication phase had already begun as seen in T31. All of the neighbor replica connected to the transaction were subjected to the replication process. Following that, the replication process data was stored in the checkpoint file as in T32. As soon as the transaction was finished, in T33, all of the copies engaged in it were unlocked and their status was set to 0. At T34, the checkpoint file was deleted, and at T35, the transaction came to an end. In this research, a synthetic dataset was employed for the experimental evaluation instead of a dataset derived from an existing database system. The synthetic dataset was generated to simulate the structure and characteristic of the throughput database transaction without being tied to any specific application domain. This approach was chosen for two main reasons. It provides full control over transaction design, application distribution, and failure injection, thereby ensuring that test scenarios accurately reflect the target failure conditions, which is the neighbor replica failures in this experiment. And it eliminates dependency on priority or domain-specific dataset, which may introduce bias or limit the generalizability of the results. The synthetic dataset contains transactions with varying read and write operations, which were systematically distributed across multiple replica sites in accordance with the binary void assignment on grid protocol. Failure events were artificially introduced into the transaction flow to test how BVAGCR performs in failure. Although the dataset does not originate from a real-world application, it effectively captures the essential behaviors of the distributed transactions in a replication environment, making it suitable for benchmarking and validating the proposed models. Synthetic datasets are widely adopted in distributed database and fault-tolerant research when the primary objective is to test system behavior under failure scenarios. By generating transaction workloads and replica interaction programmatically, the study ensures repeatability, transparency, and controllability in the experiments, which are essential for validating the correctness and efficiency of the proposed models. For this study, execution time is used as a key performance evaluation indicator. A shorter ET generally indicates higher system efficiency because it takes less time to execute a particular transaction. The overall ET in this context is made up of several distinct phases: before failure, transmission delay, data latency, fault tolerance, and after failure recovery. Transmission delay is the time between the end of a failed transaction and the start of its resubmission when the issue is resolved at the affected location. For consistency with earlier research, transmission delay in this study is limited to a maximum of 5 seconds and is considered into the ET for both standard BVAG and BVAGCR, as both require a waiting period during failure recovery. Data latency is defined as the time it takes for data to become available within the database system, with an ideal threshold of 0.0020 seconds or below. In this study, data latency is only incorporated in the standard BVAG because it requires waiting in a queue before obtaining a log on the necessary replica site. In contrast, BVAGCR excludes data latency from its EP calculation because it keeps exclusive logs on all participating copies throughout the transaction, including failure scenarios, removing the requirement for queuing or log reacquisition. These breakdowns allow for a more detailed comparison between standard BVAG and BVAGCR under failure scenarios, as well as an investigation of their recovery and processing efficiency. This table presents the acquisition time comparison between the standard BVAG and the proposed BVAGCR under neighbor replica failure conditions. The results clearly highlight the routine benefits of integrating checkpoint and rollback recovery in the replication process. One key observation is that before failure, BVAGCR incurs a higher overhead of 0.0707 seconds compared to standard BVAG, which has 0.0079 seconds. This additional time results from the checkpointing process, where every detail of the transaction is periodically stored in the checkpoint file. While this introduces overhead in the before failure phase, it plays a critical role in enabling rapid recovery after a failure occurs. During failure recovery, BVAGCR demonstrates a significant advantage. In the fault-tolerant phase, BVAGCR requires only 0.0096 seconds to retrieve transaction details from the checkpoint file, whereas standard BVAG lacks such a mechanism. Consequently, after failure, BVAGCR resumes execution in only 0.1867 seconds compared to 3.3183 seconds for standard BVAG. This difference is substantial as standard BVAG must restart the entire transaction from the beginning, while BVAGCR resumes directly from the last consistent checkpoint state. Overall, the total ET of BVAGCR, which is 5.2607 seconds, is considerably lower than that of standard BVAG, which obtained 8.3282 seconds, representing an improvement of approximately 36.74%. This improvement underscores the efficiency of integrating CR into the replication process, as it minimizes downtime, reduces waste computation, and accelerates recovery in failure-prone environments. The result also demonstrates that while BVAGCR introduced additional costs in the before failure phase, these costs are negligible when compared to the significant time saving achieved in after failure recovery. In distributed database system where failures are likely to occur, the long-term benefits of reduced recovery time far outweigh the small initial overhead. Furthermore, these findings provide evidence that CR enhance not only execution time, but also the reliability and robustness of the replication protocol. By ensuring that transactions do not need to be fully restarted, BVAGCR reduces the risk of cascading rollbacks, minimize resource retention, and improve the stability of the overall system. In summary, the experimental results validate that BVAGCR provides substantial improvement over the standard BVAG in neighbor replica failure scenarios by leveraging CR for state-based recovery. This demonstrates the potential of hybrid application models to achieve both efficiency and resilience in distributed database environment. As the conclusion, this study used the checkpoint and rollback recovery fault-tolerant approach from the BVAG-CR database replication model to handle database replication transactions in the event of neighbor replica failures. The addition of CR enables BVAG-CR to outperform the standard BVAG replication technique, particularly in terms of reduced execution time during failure recovery and transaction re-execution. These findings illustrate the benefits of combining structured application systems with strong fault tolerance measures. From a wider viewpoint, The proposed BVAGCR model addresses one of among a crucial encounters in distributed system, ensuring reliability without compromising efficiency. The incorporation of checkpointing and rollback mechanism not only quickens recovery but also strengthens the resilience of the application progression against unforeseen node failures. As modern applications demand continuous service with minimal downtime, such approaches can play a vital role in supporting mission-critical systems, including economic platforms, healthcare database, and extensive cloud infrastructures. However, some limitation remains. Since checkpoint rollback recovery requires periodic checkpointing, additional storage overhead and processing time are incurred during transaction execution. Furthermore, BVAGCR still depends on the failed replica being repaired before the system can fully resume normal operations, which may increase downtime in prolonged failure scenarios. Another limitation is that the model was primarily evaluated in a controlled neighbor replica failure setting, and in its scalability under diverse workloads or multi-site heterogeneous environments was not extensively tested. For future work, the integration of alternative fault-tolerant techniques such as priority-based recovery or task resubmission can be explored to complement CR, further minimizing downtime and reducing reliance on failure repair times. Additionally, extending BVAGCR to cloud or edge computing environments would allow assessment of its effectiveness in real-world distributed infrastructures. Performance metrics beyond execution time, such as energy efficiency and network utilization, can also be incorporated to provide a more comprehensive evaluations of the model's resilience and efficiency. That concludes my presentation. I am deeply grateful for the opportunity to share this today. Thank you very much.
Okay, so thank you so much for this presentation. Thank you so much, Dr. Sharifah, for your PhD student presentation, for the comprehensive and technically detailed presentation. So, Dr. Sharifah, are you here? Oh, no, Sharifah, no, Dr. Noazia, all right. Okay, so we have a question, I think, in the chat box. So the question is, could this model be integrated with blockchain-based database replication for enhanced security?
Okay, Assalamualaikum. Thank you, Dr. Nurziada. Okay, and also Miss Nur Amalina for the question. Okay, I will say that it's a great question. Could this model be integrated with blockchain database? Of course, inshallah. Actually, we got the fund until 2027 to enhance our replication model with blockchain database. The university support, the industry support. Okay, so basically, I wrap up again. Okay, what Sharifah presented. Okay, what our team presented. So actually, we are doing distributed database in replication. Kita replicate data dekat beberapa database dengan syarat dia ada network lah. So itu distributed database. Dan kita replicate data tu tak dekat, kita tak replicate data to all site. We are replicating data to some site, certain data to certain site. So the storage is minimum, and then we also mine the data where the exactly attribute that needed will be replicate at the same server. Contoh kan, kalau kita ada attribute A sampai Z, so kita tak replicate A to Z dekat semua server. Kita replicate ikut quorum. So katakanlah kita ada A, B, C, D dekat server A. Kita ada server, kita ada data E, F, G, H dekat server B. Okay, so A, B, C, D, dia transaction tu pakai sekaligus bila kita mine the data. So sebab tu kita kita letak kat satu server, baru speed transaction tu perform. Dan apa yang berlaku bila sebab ini adalah synchronous replication. Synchronous replication means data tu kita replicate dekat semua quorum replika immediate, serentak. So dalam fasa kita nak replicate data tu, dia ada initiate lock, propagate lock, obtain quorum, release lock and commit. So baru data tu strict replicate lah, consistent. Sebabnya kita nak pakai untuk strict semantic data. Strict semantic data ni macam agak bahaya lah. Contoh kalau transaction banking, boleh ke kita bayar dekat sana tengok tak bayar lagi? Tak boleh kan? Kita kena immediate. Tapi kalau asynchronous, kita replicate malang karang pun tak apa. Contoh data dekat library, buku dekat library. So yang tu tak adalah ad hoc sangat. Kita nak tengok dekat jiran, branches, data terkini pasal buku yang baru beli sampai hari ni. So itu kita boleh buat malam. Tapi kalau transaction business, transaction banking, itu strict semantic data. Dan yang menjadi masalahnya bila pasal transaction tu berlaku, tiba-tiba crash. So yang BBAG yang original tu kita tak buat untuk crash. Kita buat untuk apa dia panggil? Normal transaction. So sekarang kita consider untuk crash, kita bind dengan checkpointing recovery service dan masa dia fail, so dia akan letak status itu yang banyak. Dia punya formulation, normalization tu, notation. Banyak sangat cara nak solve transaction, two-phase commit, two-phase locking, and then kita consider untuk asynchronous case bila berlaku disaster. Dan kalau kesesuaian dengan blockchain database ni, blockchain ni kita nak pastikan data tu sentiasa secure, sentiasa konsisten. So apa yang berlaku ialah kalaulah katakanlah transaction ada yang transaction tak sama kan, dia kena check quorum. Kalau transaction tu tak sama, maksudnya tak betul lah tu. Ada intruder ke apa ke kan. So sebenarnya kita baru nak venture on the part security part. Cuma kalau original BBAG dulu kita buat, memang kita ada guna SSH key, dia kena pergi ketuk pintu sebelah, check dulu key correct tak, ada encryption, decryption balik. Tapi kita tak buat lagi untuk BBAG CR, tak ada lagi.
Okay, okay, saya faham. Sebab tu saya tengok dalam result tadi, ada checkpoint tu dia ambil sikit masa kan compared to yang original. Tapi
betul.
overall masa untuk yang part yang enhanced version lagi okay.
Betul.
Kita tak boleh kata checkpoint saja ambil masa, memang checkpoint tu kena ambil masa sikit. Tapi selepas checkpoint tu, dia punya result dia still better lah compared yang lama, betul?
Betul.
Alright, okay. Okay, so terima kasih. Thank you so much for this great presentation and also great research from this team. I think that is paper lah Alright. So thank you once again for the all of us for the excellent contribution. So ladies and gentlemen, this concludes that our network and cybersecurity and also artificial intelligence track close until here. So the topic actually presented here show how AI and also cybersecurity continue to strengthen trust, resilient and also intelligent in modern digital system. So on the behalf of this i-CAIAS 2025 organizing committee, I would like to sincerely thank you all for the presenters, for the outstanding research contribution, for the audience, for your active engagement and also a very beautiful questions. So after this, please scan QR code to get your participation certificate. So please continue to engage with the conference. We have many more exciting sessions ahead. So please be reminded that we will have the IoT workshop at 2 p.m. today, followed by the closing ceremony and best Research Paper Award at 4 p.m. So thank you once again for your participation and contribution to this conference 2025. Thank you so much. See you again. Bye.